So for Unit 3, we're going to be covering trigonometric functions for any angle. In this unit, we're going to start to see the definitions of trigonometric functions for any angle, meaning for any angle, it means we're going to use the angles in standard position and look at a point on the terminal side of the angle in standard position to define the trigonometric function. All right, so we're going to see all over again the trigonometric function. Now, notice here that you have an angle in standard position, okay? So the angle is theta, and it is drawn in the standard position, meaning you're going to put in the Cartesian plane, which is the rectangular coordinate system that we use to graph functions. You start from the positive part of the horizontal x, that's the initial side of the angle, and that we saw in the beginning of this course, which was Unit 1. So you have the initial side, all angles in standard position start from that part there that I highlighted in red. Now you rotate either, counterclockwise or clockwise a certain amount of degrees or radians that correspond to the amount, the measure of the angle. Where you stop is the location of the terminal side. So here it's showing that the terminal side of this angle is in the second quadrant, and there is a point there designated by P with coordinates x and y. Now, x and y are going to be numbers, right? It is really a location of a point that corresponds to also the position of the terminal side. So based on that point, and by the way, there are infinite many points on that terminal side. All you need is one of them, and we're going to see different ways of working with choosing points on the terminal side. So you need one of those points on the terminal side where you're going to use the coordinates and also the distance between the origin point, which is 0, 0, right? So right here we have the point 0, 0, where is the vertex of the angle in standard position, to the point P. So there's this distance, and we're going to designate this distance R, as you can see in the drawing. So the distance between the origin of the system, which is the point 0, 0, to the point on the terminal side, P, we designate by R. Now, because that is a distance, R is always a positive value. So R is always positive, right? So it is defined as a distance. 0, 0, by the way, is a point also on the terminal side, which coincides with the vertex, but we're not talking about that point. We talk any other point on the terminal side except the origin point. So we have this point on the terminal side of the angle, so we have coordinates x and y. And therefore, we also have the distance r. You can think of this as a radius. Now, because of Pythagorean theorem, if you look at the coordinates of the point, we can think that these coordinates form a right triangle. And because they form a right triangle, r is in the hypotenuse of that triangle, y and x are the legs of the triangle. So because of that, by the Pythagorean theorem, we have that r can be computed based on the coordinates of the points, which is the square root of x squared plus y squared. So given x and y, the point on the terminal side of the angle in standard position, I also can compute r. So those quantities are related because of the Pythagorean theorem. Now, again, I have x, y, and r. Our trigonometric functions will now be defined as sine as being y over r, and I will make the connection to what we did before. Cosine is going to be x over r. Tangent is y over x as long as x is not 0, because certain points on the terminal side would have the coordinate x equals 0. But for those points or those angles where x has a value of 0 for the point, tangent is not defined because we cannot take in y and divide by 0, right? So this is valid as long as x is not 0. So you get the tangent by dividing y over x. We also have cosecant, which is r over y. Remember, cosecant is the reciprocal of sine, so it makes sense that if you flip the sine definition, which is y over r, and then you get r over y, and that's the cosecant. And again, that only works if y is not 0, because if it is 0, the coordinate of the point is 0. When y is 0, you don't have a value, you cannot compute, it's undefined. We also have the secant, which is the reciprocal of cosine. So again, cosine is defined as x over r. So if you flip, take the reciprocal, that is r over x, and that's the secant. And again, that definition of secant works if x is not 0. If x equals 0, then you have undefined secant. We also have cotangent, which is the reciprocal of the tangent. So this time we have x over y. So again, y equals 0 means that is undefined cotangent. So we can get the value of cotangent by dividing x over y as long as y is not 0. And you also can see here that from our trigonometric identity from before, we have that sine square of an angle theta plus cosine square of the same angle theta equals 1. Now, if you use the definitions above of sine, so for example, sine is defined as y over r. So if you square that quantity and add to the square of the quantity that corresponds to the cosine in this new definition, which is x over r, you get that y squared plus x squared is divided by r squared. Okay, so it's just adding those fractions after you take the square. Now, y squared plus x squared comes from the Pythagorean theorem, which means r squared, right? So it comes from here that the hypotenuse square equals x squared, one of the legs, plus the square of the other leg. So if we use that, that sum on the top of the fraction, of course, is r squared. So on the bottom, you also have the same quantity, r squared. So the division then becomes equals to 1, which makes sense. So it's still a valid trigonometric identity. So meaning this new definition that now use coordinates of points on the terminal side of the angles in standard position is still applicable to the trigonometric identity that we saw before. They do not contradict that. And also, by the way, it does not contradict the definitions we saw last time in Unit 2, because if you look at the angles for the right triangle, as we did in Unit 2, so in Unit 2, let me specify, this was in Unit 2, you had the right triangle, and if I call R the hypotenuse, and let's say this is going to be X, this is going to be Y, we again have the same relationship for the right triangle by the Pythagorean theorem, which is r squared equals x squared plus y squared. So it's still a valid thing as for this new definition. So again, it's not a contradiction, it still fits there. But the angle to be inside the right triangle means that we're dealing with angles between 0 and 90 degrees. So the angle in standard position would be somewhere in the first quadrant. And again, if you take a point on the terminal side of an angle in the first quadrant, this point, when you look at the coordinates, so again, I'm going to call point P, which has coordinate x and y. So meaning this quantity on the bottom for x, and there is a quantity vertically here, which is the value of y. And the right triangle right here give the relations I mentioned before. So if you remember the angle, which is again theta, which is this measurement here, means if I have to compute sine from this position in the first quadrant, according to the right triangle, as we did in Unit 2. So if I look at this right triangle, in standard position there corresponding to the right triangle like this, where this is theta. So here's the point P of x and y. So we have that this quantity here is y, this quantity here is x, right? And again, this is r. So sine is opposite for us is y, over hypotenuse, which is r. And that's exactly the same thing that we see here. So the only difference is now I'm expanding these definitions to be useful for other angles that do not fit inside a right triangle, as in Unit 2 again. For the right triangles, we can fit any positive angle between 0 and 90 degrees, but that definition of opposite, adjacent, and hypotenuse, they do not work if the angle is negative or if the angle is beyond 90 degrees. So we could not use the right triangle as case. Now, if you use the point on the terminal side, yes, and then you have a generalized definition that now is applicable to all kind of angles, positive or negative, beyond 90 degrees. So it doesn't need to fit inside the right triangle like before. So instead of using right triangles from now on, most likely, if I need, I will refer to points on terminal side of the angles in standard position instead of right triangles. Even though implicitly I will be working with these right triangles as a way of looking at the coordinates of the points anyway. So the position of the terminal side can tell you if sine, your cosine, your tangent, and the other three trigonometric functions are positive or negative. What it's saying here in this quadrant number 1 example is that if you consider the angle in standard position and the terminal side is in the first quadrant, all trigonometric functions there will be positive. Why? Because in that quadrant, both x and y are positive. Remember that r is always positive regardless of what quadrant it is. But in quadrant number 1, you have that these quantities x and y from the point will be always positive. So the coordinates being positive for the points on the terminal side indicates that sine, cosine, tangent, they are all positive because you take a positive number, divide by positive number, you always get a result that's positive. So let me take tangent as one example here. So tangent, according to the definition that we just start to see now, based on the point on the terminal side, is y over x. Because it is y over x, so basically you're taking a positive number because this is the first quadrant and divided by another positive number. So the result is going to be that the tangent value is positive. The same thing goes for cotangent, secant, and cosecant, and of course sine and cosine. Now, what if the terminal side is in the second quadrant? Not everything is positive. We still continue with the idea that r, which is a distance, is always going to be positive regardless of the quadrant. But you can see that to be in the second quadrant, the x-coordinate of the point has to be a negative value. So this point right here is only in the second quadrant if your x-coordinate has to be negative. Now y is going to be positive, right? It's above the horizontal x. So the y value of the point is positive. So you can see here that when I look at the sine, which is y over r, basically what I have is that y is a positive value. And r, by definition, is always positive. So the result is going to be that I get something positive. So sine is always a positive number for the second quadrant. Now, let's take some other trigonometric functions. You can take a look at the others. Let me talk about now the cotangent. Now, by definition, cotangent is x over r. Now, we just saw that to be in the second quadrant, x has to be negative. So you're taking a negative number in your fraction. So to be in the second quadrant, x is negative, so you take a negative number and divide by y, which is positive. Obviously, when you divide a negative by a positive value, the result of your fraction is going to be a negative number. So what it's saying that your cotangent is expected to be less than 0, negative, for the second quadrant. So please take a look at the other trigonometric functions that are being explained there, if they are positive or negative and so on. And the third quadrant, so I'm going to talk about secant and also sine, okay, as an example here. So the third quadrant, so you have a point on the terminal side. That means to be in the third quadrant, both x and y are negative. So both x and y has to be negative. Now, when you look at sine definition, it means y over r. And remember, r is always positive. That is the thing that never changes throughout the quadrants. They're always positive r values. So for the sign definition, which is y over r, you have that y is negative. So you're taking a negative number and divide by r, which is always positive. So the result of your division, your fraction, is going to be a negative number. So we have then the sign is less than 0. It's always negative, okay? Please check cosine, check the tangent. You're going to tell me if the tangent here is it positive or negative. Now let's take a look at the secant. For the secant, we have that secant by definition is r over x. So meaning in this fraction r, which is always positive, you're taking a positive number, and divided by x, which is negative in the third quadrant. So the result of the division of the fraction is a negative number, which tells me that in this case, I have that secant of theta is less than 0, meaning negative, right? So less than 0. So please do quadrant number 4. I'm not doing, but notice that the first two is done for you. So it tells you that sine is going to be negative, cosine is positive. So you're going to analyze this and answer for all other trigonometric functions. So this is a little exercise for yourself. Let's do some of the exercise here to see how this information can be used in order to obtain, let's say, the quadrant of the angle. For example, here, part A, we have that given an angle in standard position, I want to know what is the quadrant that the angle will fall into. All I know about this angle is that cosine is positive and tangent is positive, okay? So I have to analyze based on this given information. So here's the given information. Based on that, doesn't tell me what's the angle, doesn't tell me what's the quadrant, but these two pieces of information together give me that this angle, whatever it is going to be in a certain quadrant, and that's what I want to find. Now, cosine, which is x over r, to be positive means that x must be positive. R is always positive, so there's no other way of getting this fraction positive if x is not positive. So from that piece of information, I have the cosine being positive, x is positive. Now, I also have the tangent is positive. There are two ways that the tangent can be positive. Remember, tangent is the fraction, and let me use a different color here for the tangent, is y over x. Now, this is positive if you have both numbers positive, both top and bottom of your fraction, or both numbers are negative. So the only way I can get that fraction to be positive, which is my tangent being positive, is both numbers are positive or both numbers negative, right? Now, this does not work here. Meaning it has to be this first type of tangent. So this doesn't work. It works only with the both numbers being positive, which tells me that both x and y are positive. Now, there is only one quadrant where both x and y are positive. This is quadrant number 1. Part B. Okay, so now we have the cosecant of an angle theta is less than 0, meaning negative, and the secant is also negative. So we want to know what's the quadrant, right? So what is the quadrant that the angle theta belongs to? Let's take a look at the first information. Remember, cosecant, which is reciprocal of sine, meaning you flip the sine definition, so you get r over y. If that is a negative number, according to the information given, less than 0 means negative. You know the top number here is always positive, and that fraction is negative only if the bottom number is negative, which tells me that y has to be negative. Now, using the other piece of information, which is secant, which is reciprocal of cosine, which is x over r, so if you flip, you have r over x. Again, the top of my fraction is always going to be a positive number because r is always positive. And it tells me that that number, the result of the fraction is negative, is because the bottom number has to be negative. So that's how I get the whole fraction to be a negative number. So we know that y is also negative. Now, together, I have that both y negative and x negative only happens if we're talking about quadrant number 3. So I know that theta must be in quadrant number 3, meaning the terminal side must fall in some position within quadrant number